Hi, everyone. I'm Sandy Lucas, the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us for the second session of the webinar series called Tropical Pacific Observing System Process Studies. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of our prior CVP webinar series or the previous talk in this series, I encourage you to view them from our website. Today's session will also be posted there soon. CVP supports the research that enhances our process-level understanding of the climate system through observation, modeling, analysis, and field studies. The topic of this series is the tropical Pacific Ocean, and its focus is to build upon and refine the current scientific understanding of the tropical Pacific climate system. The tropical Pacific region is important to climate variability due to its role in El Niño Southern Oscillation, ENSO, and the teleconnections to the United States weather and climate. This webinar series covers the 8 projects funded by CVP, which started in September of 2018. The focus of these modeling studies is to refine the current scientific understanding with a specific focus on 2 process studies identified in the TPOS 2020 first report. The first is the Tropical Pacific Upwelling and Mixing Physics, or PUMP, and the second is air-sea interaction at the eastern edge of the warm pool. Outcomes from these projects will be used to further the development of possible field campaigns in the tropical Pacific region. I look forward to hearing the results from these projects in the webinar series. I'd like to thank Jose Algrin, the CVP program specialist and the organizer of this series, for all the hard work that he has done putting it together. At this point, I will turn it over to Jose for the full introduction of this series and the introduction of our speakers today. Jose, when you're ready.
Thank you, Sandy. Hi, everyone. My name is Jose Algrin, the program specialist for the CVP program here at NOAA. Welcome to the second of 5 webinar sessions on the topic of the Tropical Pacific Observing System TPOS process studies. Each of the sessions will feature 2 presentations and will run until November 10th, 2022. This series of presentations will share the latest results from these projects and will allow the researchers to discuss the importance of their work, outcomes, and lessons learned with a broader scientific community. We hope you enjoyed today's talks and ask plenty of questions. Speaking of questions, if you have one for the presenters, please use the raise your hand feature on the right, which you can find on the control panel. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using their audio. You will need to unmute yourself after I do so. If you have audio problems, I will ask you to type your questions in the questions box, which can also be found on your control panel. Now, we go to our first presenter, which is Dr. Donxiao Shang. Dr. Shang is a principal researcher scientist of the Cooperative Institute for the Climate, Ocean, and Ecosystem Studies at the University of Washington, and also part of NOAA's Pacific Marine Environmental Laboratory, or PML. He studies ocean circulation and its impacts on climate variability and the multi-scale air-sea interactions with observations from moored buoys and uncrewed surface vehicles, USVs. He has led and co-led a number of USV saildrone observations, including the Tropical Pacific Observing System and the Atlantic Hurricane missions. Dr. Shang, thank you so much for joining us. At this time, I will turn the controls over to you.
Thank you, Jose and Sandy, for this opportunity. Hi, everyone. I'm going to present show my screen. What do you see? Were you able to see my screen?
Yes, we can.
So my laptop or my monitor, sorry.
We can see the presentation very well.
Interesting. So I cannot see that.
We can see the PowerPoint if you put it on presenter mode.
Do you see my first slide?
Yes, we see the PI names with their affiliations.
Oh, this is not the first slide. Sorry. All right. Sorry about that. So I'm going to present the progress of integrating uncrewed surface vehicles, in particular the sail drones, into the tropical Pacific observing system. Some of you may have seen part of the presentation, since it's largely based on what Megan Cronin presented in a recent briefing to the uncrewed system program within OMAO. Our work has been funded through a series of pilot projects like GOMO, CVP, OMAO, and Ocean Exploration and Research. This is a large team effort. The PIs include physical oceanographers like Megan and me, meteorologists, ocean biogeochemists, modelers, engineer, data IT scientists, and we have international partners from Mexico and France who have been really helpful for EEZ permit applications. A little background on why we were interested in USVs. The Tall Triton Mode buoy array has been the backbone of the tropical Pacific observing system, providing the real-time observations critical for ENSO seasonal and subseasonal weather prediction around the globe. With the decommission of the NOAA ship Kaimi Moana, which was dedicated to tow maintenance in 2012, the data return of many tow moorings had been dramatically reduced, many of which were below 60% between 2012 and 2014. In response to such a crisis, an international TPOS 2020 project was formed and tasked to provide recommendations to incorporate new technologies to make TPOS more capable and resilient. The left column shows the current capabilities of the moored array. The right column are the recommendations made by TPOS 2020. While more moorings were recommended in the Western Pacific, the rather regularly spaced moorings in the Central and the Eastern Pacific are to be reconfigured to address the needs of observing RTCZs. In addition, each mooring is recommended to be equipped with surface current meters and downward solar and long-view radiometers so that the net surface heat fluxes at each site can be calculated. The CO2 flux measurements will still be limited to a few sites on the equator. Recognizing the inadequacy of once-a-year ship transect to characterize the meridional structure of the CO2 fluxes, USVs are recommended to fill in the gaps. USVs could also provide air-sea interaction observations across fronts and eddies, which cannot be made by current TPOS observing platforms and has been more recognized recently as the important missing piece of the puzzle in tropical air-sea interaction. Sail drones are one type of USVs that are manufactured and maintained by Sail Drone Incorporation. They rely on wind for propulsion and solar for instrumentation, communication, and navigation control. Because of using renewable energy, they have extremely long range and endurance. In FY 16 to 19, are you able to, do you see the screen here? Or do you want me to move away?
We can see your mouse. We cannot see any other screens other than your slides.
Okay, now it's good?
Yes, it's good.
All right, we worked with the Sail Drone company and developed the Sail Drone into an air-sea interaction observing platform. We added ADCP and the air-sea surface flux measurement capability to the Sail Drones. Most importantly, the funding also supported 5 Sail Drone missions in the tropical Pacific between 2017 and 22. each with 2 to 4 cell zones lasting between 3 to 8 months. Since these are pilot studies, a lot of tests have been done in different parts of the central and the eastern tropical Pacific, where winds are weak, currents are strong. The goal is to evaluate and improve the capabilities of the cell zone in different conditions so that they can be integrated into the TPOS. A recently funded CVP project led by Yolande Serra and Samantha Wells will further analyze these pilot missions and recommend sampling strategies for future TPOS field campaigns. We have also developed a research to operation transition plan, which will fund the TPOS 2023 mission to work together with the fishery. This figure shows all the 5 TPOS missions with tracks of each zone. 2 bases have been used for launching and retrieving TPOS cell zones. One is San Francisco, where the cell zone company is located. The other one is Honolulu, which is closer to the central tropical Pacific, particularly near the eastern edge of the warm pool and the tall 140 West and 150 West mooring. These are the long transects. Let's zoom in the TPOS 2019 mission near the equator between 5 south and 5 north. 4 cell zones maintain a perfect formation to observe the equatorial currents and the passing TIWs. The upper left panel is a screenshot of the mission portal showing HICOM predicted SST and surface currents through which we control the cell zones in near real time. The lower middle figure shows the observed wind vectors, mostly southeasterly trade, while the left and right figures show the surface current vectors of equatorial divergence, indicating strong upwelling at the moment. The mostly northward flow along the meridional section are associated with the cusp of the TIW, and the southwestward and westward currents at the leading edge of the TIW front are associated with the anticyclonic vortex of the previous TIW that's past this section and now to the west of this section. The current vectors are color-coded by the errors if currents are ignored in the flux calculation. For latent T flux, the error can be up to 30 watt per meter square, while for the wind stress, the error can be up to 0.05 Newton per meter square, which is rather significant. Further zooming in on the equator, 2 cell zones were even able to circle around the tall 140 West mooring for about 2 weeks. Not surprisingly, the observed eastward equatorial undercurrent was aligned with the thermocline. With only a few subsurface salinity measurements, we can only roughly estimate the Richardson number, which is an indicator of mixing. The lower left figure shows the temperature, salinity, and density profiles. The solid and dashed profiles were separated by 12 hours. Their corresponding n squared times 4 and the current share squared profile show the depth range where Richardson number is below 1/4, where the mixing is occurring. The lower right figure shows the time depth section of the Richardson number. Beside the strong mixing in the thick mixed layer in the first 2 to 3 days of August, the mixing tends to occur near the top of the EUC. However, the almost perfect formation of the cell zone fleet was not possible in the Eastern Pacific in late summer and fall, especially during the La Nina years, where TIWs are much stronger. The lower figure shows the struggle of 2 TPOS 2022 cell zones in the last couple of weeks. While we lack the cell zones to sail equatorward along the 125 west line, the strong westward currents formed by the chain of TIW vortices made the 2 drones drift westward, while one drone eventually reached the equator by giving up fighting but going along with the currents. The other drone had to return northward before ending the mission. The pilot studies also include the continued development of a sensor suite and capabilities. The figure shows the standard sensor suite of the sail drone. Its measurements include 14 essential ocean climbing variables defined by WMO. It's truly a multidisciplinary platform for Earth interaction observation. In FY22, we tested the direct covariance wind stress calculation against bulk fluxes. We are integrating and testing new IR radiometers. This is because the currently used Appli sensors are obsolete and the manufacturer is closing down and stopped new production. And in FY23, we will form new partnership with the NOAA Pacific and Island Fishery Center to operate a pair of sail drones in tandem, one with ADCP and one with Echo Sounder to incorporate fishery measurements in TPOS. The 3D wind sensor on top of the wing, coupled with the IMU installed inside the wing to track the high frequency motion of the wind sensor at 20 Hz, allowed us to calculate the direct covariance wind stress, which compared favorably with the bulk fluxes. The core bulk flux algorithm was largely developed from the ship-based direct covariance measurements in the tropical Pacific. So the good agreement may not be surprising, but the sail drone could greatly expand the database of direct measurements of wind stress that can be used to further improve bulk flux algorithm for wind regimes that are not common over tropical oceans. Calculating air-sea heat fluxes require the skin ST rather than the bulk ST, often measured at the top 5 meters of the ocean. The core flux algorithm applies a 1D model to estimate the skin ST. We found that by measuring air-sea heat flux and wind stress, we can extrapolate the bulk ST to not only the ocean skin temperature, but also to the foundation ST. By removing the diurnal warming, the foundation ST can be used to better identify the sharp front, such as the one experienced on December 7th, right here. It also becomes apparent that the peak on December 17th was caused by an ocean eddy rather than the diurnal warming, this peak. The sail drone's high-frequency measurements also make it possible to measure and characterize the small-scale atmospheric processes such as cold pools. The atmospheric cold pools are small-scale convections often develop at the edge of the mesoscale convecting storms. They can self-organizing and even feedback and feeding the mesoscale system development. On November 17, 2019, 4 sail drones surrounded the tall 9 Ngos 140 West mooring and formed a mesonet of about 30-kilometer box to measure a cold pool event. To illustrate the scale, the mesonet box is placed in a 5x5, 2x5, 2.5, and 1 degree domains with 1/10 degree unmarked satellite precipitation and a 1/4 degree ERA5 reanalysis wind. All 5 platforms measure the sudden drop of air temperature and the increase of wind speed associated with the cold pool, which passed the mesonet in about 1 hour. Altogether, Wells et al. Identified 276 cold pool events from the first 3 TPOS sail drone missions. The composite cold pool event suggests the enhanced latent and sensible heat flux of about 60 watts per meter squared in just 10 minutes, which is quite amazing. Some mesoscale fronts in the ocean are also observed by sail drones. The top panel shows the well-known feature of enhanced surface wind over mesoscale SLT front. The enhanced wind generally are over warmer side of the front. In this case, it's the TIW. However, the SLT front identified by the cell drone data is about 1 degree jump within a couple of 100 meters, rather than the gradual change over 60 kilometers as suggested in the satellite product. The cell drone tracks from 1.4 to 2 degree north is shown in the SLT map. This really redefines what it means to be a sharp front. A quote from Ian Cronin. Data delivery and display is just as important as observation. PMEL has developed a prototype interactive dashboard for USV data. The users can freely select the variables and examine them before downloading the data. The 3-time series shown here are the air temperature, relative humidity, and SST of the TPOS 2022 observation, just completed about a week ago. Many of the sudden drops of air temperature and the increase in relative humidity are associated with the storms and cold pools, as we discussed before. The sharp SLT front are also evident with the 2 drones were navigating across or along the TIW vortices. Lastly, a community effort is pushing the USV observation network beyond TPOS to the global ocean. A quote from Adrian Sutton: "We hope to build a community of practice for an uncrewed surface vehicle network for Ngos through an endorsed UN Ocean Decade project." Thank you. This is my last slide.
Thank you so much, Dr. Shang, for that excellent presentation. Now we're going to open up the floor for questions from the audience. Remember, you can raise your hand and I will unmute on my side. I don't see any questions so far, so I'll ask one on my end. What will be some challenges that you and your team has faced in performing this project, Dr. Shang?
I think the biggest challenge we are facing is how to prove that the data we collected are valuable. Well, as an observationalist, we really want our data to be used by the community. So we really encourage anyone that want to use data to talk to us and collaborate with us. We work together.
Okay, thank you. I see that Anish has a question, so I'm gonna unmute Anish and go ahead and ask your question, please.
Can you hear me okay?
Yeah, hi Anish.
Hi, thank you for the presentation. I don't know if my video is on. So my question was, do you know of capabilities to combine these vehicles with like either upward looking or some way to observe the atmospheric boundary layer co-located with these vehicles, like all the way to the top of the boundary layer or even some part of the troposphere, over the ocean?
Yeah, right now the cell drone doesn't have the capability, but there are some low power lidars can be installed on the platform. I guess it could be a future development.
Okay. Do you know?
I guess in order to observe the lower atmosphere, the upper the boundary layer, we need to coordinate with other platforms. In the tropical Atlantic, we are mirroring the storm development. What we do is to coordinate with the hurricane hunters, where the drop zone will be launched from those planes, so that we can obtain co-located measurements from cell drone in the air-sea interface, the gliders and Argo flows in the subsurface, while the drop zones from the airplane.
Okay, thank you.
Frank has a question. Do you want to go ahead and ask it, or should I read it out loud? I unmuted you, Frank.
Okay. Dongja, did I hear you say that the manufacturer Saildrone was shutting down production?
No, this is only the radiometer sensor. So the long wave radiation sensor is shutting down. So we have been using their sensor not only for Saildrone but also for almost all the NOAA buoys. So we are testing the same sensor.
Okay, you gave me a scare there. That was okay.
Sorry about that.
All right, I see that Muying Wong has a question. I'm gonna unmute you.
Yeah. Hi. Dongxiao, nice talk. I do hear you talk about when the Saildrone tried to follow the line, but the current was too strong, so drifted. So what's the limitation of the current? I mean, do you know, like, what's the threshold? If the current below a certain number, then the Saildrone can sail through. Do you have idea?
We have a rough idea because from the past missions, we know that the efficiency of the wind power to push the Saildrone motion is about 10 to 15%. In other words, if you have a 10 meter per second winds, you can end up about 1 meter per second Saildrone velocity. That is about the limit you can use to against the currents. While in the tropical Pacific, very often you will find the currents above 1 meter per second. So that gave us the challenge. Well, a more detailed analysis actually will be done by Yolanda Sarah and Samantha Wells. So in the next couple of years, they will do further analysis of the efficiency in different situations. What the number I quoted you is just the overall efficiency we got.
Isa Elias has a question. Let me unmute you. Okay, I'm going to ask the question for Isa. Thank you for your presentation. What sensors would you add to the Saildrone, if any?
Well, there are many sensors we want to add. So currently, the ADCP is 300 kilohertz. The range is about 100 meter. So we would like to have a longer range of ADCP. We also want to have a higher frequency ADCP, which can be used to measure the mixing better than the 300 kilohertz. And also, as Anish asked, it would be great to have some capability to measure the wind profiles. And there's technology available that we can rely on. But in addition to those sensors, we also want to add a small electrical motor that can give us additional push when we are needed.
All right, I don't see any more questions. Thank you, Dr. Chan, for that great presentation, for answering those questions from the audience. We are gonna move on now to our second presenter of the day. He is Dr. Yishun Xu from NOAA's Climate Prediction Center, CPC. He is a meteorologist with CPC within the National Center for Environmental Prediction, or NCEP. His research interests include climate prediction and modeling, and Earth-sea interactions at various timescales. He also works on ocean data simulation and some TPOS-related observing system experiments. Dr. Xu, thank you so much for joining us. At this time, we will turn the controls over to you.
Sure, thank you. So, can you see my screen? Okay. So can you see my screen in present mode?
Yes.
Oh, that's cool. Yeah, thanks for the opportunity to present our results here. So as host introduced, I'm Jason Zhu from Climate Prediction Center at Ngos, NCF. So here I will present results about OC study on the roles of tau and argo in the tropical Pacific observing system. So this result is the outcome of a CVP proposal for which Aaron Kumar, Adventure Mehar, Megan, Coroni is served as co-PIs. So, for this project, we have a lot of collaborators. In addition to the PIs, the investigators for this proposal, we additionally got lots of help from some DA experts, including Guillaume Travers, Daniels, and also the EMC Marine DA teams. I also personally got some help from Gender Wang and Wenju Wang in setting up my natural runs. So for this talk, I will firstly give a brief background for my work and the TOPS 2020 project. Then I will introduce my experiment setup and the results. In the end, I will give a brief summary. I still use 2 slides from Dr. Billy Kessler for introduce my background. As Dongxiu also mentioned, the background about the Tropical 2020 project. We have seen lots of crises for the current tropical Pacific observing system. The first one is 2012 to 2014 tau crisis. At that time, the maintenance ship is retired. The data return for tau reduced significantly during that period. Another problem is about the treatment in the Western Pacific. Since Japan reduced the investment in treatment, so since 2017, there is just one of treatment mooring left at the Western Pacific, equatorial Western Pacific. On the other hand, since the completion of tau, they have many new observing capabilities. So one of them is the argo. It already have more than 4,000 globally. It has become an important component of the tropics observing system. So on this background, the community introduced the Tropics 2020 project. So it is to recommend, it is to give a tropical Pacific observing system and propose a redesign of the system and make it more effective, more modern, and robust. Our work is as a support of this project. We will conduct some OC studies. In particularly for this talk, I will present our results about the role of in situ tropics observations in the current tropics. We will focus on the roles of tau treatment and argo. All my materials to be presented are based on our paper published last year. If you want to see more details, you are encouraged to look at this, over there. So as in all observing all OC studies, we need a natural run. Our natural run is based on modified CFS-V2. There are 2 major modifications relative to the operational CFS-V2 in our experiment. The first one is about the atmospherical convection schemes. This modification is modified about the MJO simulations. As shown on the left side, here presents the propagation of MJO-related convections in colors. So in observations showing the up left, you will see the MJO-related convections can propagate eastward through the maritime continent. When we use the south convections as in the operational CFS-V2, the MJO-related convection stopped before the maritime continent. So we tried with the another convection scheme named ROS. So after the modifications, the propagation is get improved. So our another modification is about the ocean part. We increase the vertical resolution of our ocean. So in the operational CFS V2, over the upper ocean, the vertical resolution is 10 meters. We increased it from 10 meters to 1 meters over the upper 10 meters. So this modification is try to address the diurnal cycle. As you see the figure on the right side, you can see compared to observations, our diurnal cycle is very well simulated. So another bullet here shows the general resolution in our natural run. So for atmospherical, the horizontal resolution is around 100 kilometers. Vertically, we have 64 levels. For ocean, the overall resolution is half degrees. Within equatorial region is quarter degree. After we enhance the vertical resolutions, we now have 50 levels. Over the up 10 meters, it's 1 meter. This slide shows another evaluation about our lateral run. On the left side, it shows the simulation of Ngos. You can see there is irregular Ngos type of variability in our coupled system. But on the right side, it shows the barrier thickness simulation compared to the coarse vertical resolution in the middle. Our simulation of the bottom is clearly better than that, is close to the observations. Our data simulation experiments is based on the Ngos, which is under active development at the NCEP with contributions from the Joint Center for Satellite Data Simulation. So the Ngos is a JDA-based ocean data simulation system. So currently we still use 3D for our experiments, but more advanced DA algorithm is on the test for Ngos at the NCEP. Based on this DA algorithm, we have adopted completed a 40-year analysis with 1 degree configuration. The table on this corner, it shows the data set we assimilated in this 40-year analysis. As you can see, we as the Ngos can assimilate almost all type of ops, including satellite trimetry, satellite sea surface temperature, and sea surface salinity, and also temperature and salinity profiles. We can also assimilate sea ice concentration. This slide is a brief evaluation of Ngos. We compare it with two current NOAA ODA systems, including GODAS and CFSR. The validation is compared against objective analysis, UK Major Office EN4 analysis. So on the left side, we're showing the mean difference along a vertical section in the equatorial Pacific. On the right side, it shows RMSE. For each side, the left is for temperature, the right is for salinity. We can see no matter in mean bias or RMSE, Ngos show improvements in both temperature and salinity relative to GODAS and CFSR. So now let's describe my experiment setup for my OC studies. As mentioned earlier, so this experiment is based on Ngos. For the forcing for my experiments, all taken from my natural run with daily mean fields. The synthetic ops to mimic the tau and Arco distribution is also generated from my natural run. For tau, in the figure showing below, the green squares represent the current tau distributions. So tau summary, we summary it every 24 hours. That is because our data assimilation cycle is 24 hours. So we didn't summary it as high as the reality. So the tau distribution is generally follows the real tau distribution, both on the horizontal direction and the vertical direction. For Argo, we didn't follow the real distribution, but use but based on its typical distribution in a simple way. So we sum it every 3 times 3 degrees boxes and every 10 days. But vertically, we follow a general Argo summary resolution. Here is the list about our experiments. We have conducted 4 sets of experiments. The first one is called NoDA. In that experiment, we did not assimilate any synthetic orbs. We tried to treat this experiment as our reference and to see how much our lateral run can be reproduced by prescribed atmospheric forcing. Our second experiment is current TOR. In that experiment, on top of NoDA run, we assimilated the synthetic temperature profiles and a few salinity profiles every day with the current TOR configurations. The third experiment is experiment Argo. So in addition, on top of NoDA one, we assimilate the Argo profiles. Generally, it's temperature and salinity profiles every 3 degree times 3 degrees and every 10 days. So the last experiment, we assimilate both synthetic TOR and Argo profiles. All these experiments we conducted for 5 years and studied after 30-year model spin up. This assimilation is conducted once per day. So one focus of our proposal is about multiple time scales. So when we analyze our results, we try to evaluate this variability at different time scales. Firstly, we look at the mean bias, which is calculated as the 5-year mean status. When we look at the variability, we remove the mean bias first, the climatological mean status first, then decompose the daily anomaly into 3 components. As here is a figure here, it shows the example for our decompositions. The black curves represent the raw daily anomalies. The red curves represent the low frequency variability, which is defined as the 91 days running means. The green curves represent the intraseasonal variabilities, which is defined as the difference between 21-day running means and 19-day running means. So the remaining component is defined as the high frequency variability. So now let's look at our results. This is the comparison of the mean bias. So on this figure, on the left shows the difference in temperature. On the right shows the difference in salinity. The first row is the no data assimilation run. The second one is for run assimilating synthetic TOR profiles. The third one is for the Argo experiment. The bottom row is for the assimilating both TOR and Argo profiles. So it's a vertical section along the equatorial Pacific again. So in no data assimilation run, we can see there are large biases. Basically, at the subsurface, we see the ocean is very cold than our lateral run. On near the surface, it's warmer. Well, the water also very too fresh. Once we assimilate the TOR profiles, this bias in temperature is removed significantly. For salinity, we have some sampling at 5 TOR moorings along the equator, so over the up 150 meters. So over this region, the freshening bias is removed. However, below that depth, the bias is still there. For when we instead assimilated the Argo profiles, we see not of bias is removed. When we assimilate both, this result is almost comparable compared to we assimilate Argo itself. Now let's look at the low frequency component. So in addition to the RMSD in the left, on the right side, we also show the standard deviation of temperature and salinity at this time frequency in our natural run. We use this plot to present the signal, to amplitude of our signal, which is to be reproduced by our data simulation experiments. When we look at the no data simulation run, we can see the RMD is significantly lower than the signal amplitude. That means the no frequency can be mostly reproduced by the purely prescribed atmospheric status. When we assimilate the tau profiles, but in the no data simulation run, but we still see a not of bias at the subsurface in both temperature and salinity. When we assimilate the tau profiles, this bias is significantly removed. If we assimilate tau profiles, the improvement is even larger. Here is for the intraseasonal variability component, the intraseasonal variability component. The result is similar as that for low frequency component. So not of bias is removed by no data simulation. When we assimilate tau, the improvement is not very clear. The only improvement we can see is at the mooring sites, but between them we still see large bias over there. However, when we assimilate tau profiles, this improvement is significant in both temperature and salinity. When we assimilate both tau and argon, the result is comparable to we purely assimilate argon profiles. The results for high frequency component looks different. If we compare the no data simulation run and the amplitude of a signal, we can see they are comparable. That means this high frequency component cannot be well reproduced by the prescribed atmospheric forcing. That could be understandable because the no high frequency component variability is driven by the internal ocean instability other than atmospheric forcing. When we look at the tau and argon simulation run, we can see both of them is harder to reproduce this component variabilities. So it could be because for tau, even though we have very high sampling temporarily, but especially it is too coarse to reproduce this high frequency variability. For argon is opposite. For temporary, it's too coarse. 10 days may not good enough to represent such a variability. Is about currents. The currents is most diagnostic check out about the strict evaluation because it is not a data simulation variable in our experiments. So the figure on the left compares the mean status of currents with the first row for the current itself for natural run. On the left column is the whole currents for our experiments. The left column is the difference relative to natural run. On the right side, we show the RMSD on the low frequency component and the intraseasonal component. The overall message over here is argon is basically better than tau in constraining currents. So the reason we understand is that because most of tau sites didn't sample salinity. So when we assimilate tau profiles, salinity is not assimilated. So there will be large bias in densities. So that could result in large density bias in currents as well. So here is my summary. So the main message here, the mean states low frequency and the intraseasonal component of tropical salinity could be well captured by assimilating argon profiles. As a result, the currents can be well constrained. That's what I have. Thanks.
All right, thank you, Dr. Xu, for that excellent presentation. I'm going to open up the floor now for questions. I do see one on the chat from Shidong Shang. He asked, your DA cycle is 24 hours. Does this mean your DA does not resolve the diurnal cycle?
Yes, Dongxiao. Yes, for this moment, we assimilate our data sets once per day, so we cannot resolve diurnal cycle in our experiment. On the other hand, the current setup at the EMC, the data assimilation cycle is 6 hourly, so it could partially resolve the diurnal cycle in that setup.
Okay, I see that Charlotte DeMont has a question. I'm gonna unmute you, and please unmute yourself on your side.
Okay, now I'm unmuted. Thank you. Yeah, thanks. This was just a really fantastic talk. So on most of the timescales you analyze, there are still, it's very difficult to reduce the errors near the surface, right? And some of that has to do with the vertical resolution of the measurements, maybe the vertical resolution of your model. But what are your thoughts for how those can be reduced? Because clearly this is a lingering problem for trying to simulate or model the convection that's in contact with the upper layer of the ocean.
Yes, thanks for the question, man. So I think that for Tor and both Tor and Argo, the way I'm assembling, so still have very close vertical resolution near the ocean surface. So I think that's the issues for that could be an answer for your question. So we cannot reduce the bias over the near surface. However, in the real world, we could use the satellite SST to reduce such bias, I think. Hope I answer your questions.
Yes, you did. Thanks so much.
Thanks.
I see one question on the chat from Frank Bryan. Are the synthetic Argo floats all profiling on the same day, 1 out of 10, or are they randomized?
That's a good question. Yes. So for now, we still use a very simple way to sample the Argo distribution. If they were sampled at the same day, that could bring some uncertainties for our results. So, but our way follows a typical distribution of Argo. So the current Argo, actually the current Argo, it could be higher than, has higher resolution and then the way I'm sampling over the equatorial region. But the standard typical distribution is around this. So I think the problem about will be addressed in our future experiments. We are trying to do some real observing experiments. So assimilating the real Argos to do some data design experiments. Yeah, at that time we could see how the way of sampling Argo affect how much uncertainty it could bring in our results. Yes, we noticed that issues.
Okay. Any other questions for Dr. Xu at the moment? Going once, going twice. All right, so we want to thank now both our presenters, both Dr. Xu and Dr. Shane, for those excellent presentations. And thanks everybody for joining us today. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/CVP. We hope that you will join us for our next webinar. It'll be Wednesday, not Thursday, Wednesday, October 19th. That will feature two more panelists, Kelvin Richards from the University of Hawaii. He will be presenting capturing small vertical scale features in observations and models and their impact, and Anish Subramanian from the University of Colorado Boulder, formerly from Scripps. And the title of his presentation is Improved Understanding of Forecast Biases and Errors in the Tropics Using observing system experiments. Once again, thanks everybody. It's Sandy, if you have any last words.
Thank you, everybody, for presenting, and I look forward to seeing you all on Wednesday, October 19th.
Thanks, everybody.